right assumption that the sun was, all the stars were like the sun, basically, and certain other wrong assumptions. He was a very vain man. And he was quite confident that when he looked in with his eye, he could see the angular size of a star. In fact, it's impossible by a factor of 1,000,000, but he thought he could do that. Therefore, he thought he was seeing the disk of a star that was the size of the sun, and using something called the small angle approximation, he was able to conclude that the stars were so close they had to have a parallax, and therefore Copernicus couldn't be right. Now, I have 3 slides in the course of this talk where I will give you the questions of the day. So this is what drives people to build better telescopes, besides just the availability of technology. So by 1650, the question was, what these questions would have been current. Does the Earth move at all? Not does it go around the sun, does it move? Are the stars like the sun? These are pretty basic questions, which probably you've never even thought about because you were taught from the 2nd grade that we know the answers to these things. How far away are the stars? And by the way, if the Earth orbits the sun, how does it keep the moon attached to it as it goes around? There's no concept of gravity. And where was that missing parallax? These were great mysteries, and the scholars of the church simply said, Galileo, you're a scientist. You know that if you make predictions and they aren't confirmed, you got to go get a new hypothesis. So this went on for 100 years. Now, in terms of technology, I showed you that the lenses were not very good, and there was a great problem with making big lenses better so you could see fainter. Galileo knew he wanted to see fainter. And as today, the more expensive you make things, or the bigger you make them, they get more and more expensive. By 1640, it was realized that the atmosphere had something to do with the size of a star image. All the amateur astronomers in the room know about this. And this, it turns out, I finally concluded after a couple of years of looking into it, this is the big persistent technology problem that never got solved. And I have the date 1980 for reasons that you'll see in just a few minutes. So we have not been able to see tiny stars, the true angular resolution of stars, and over this whole period. Now you're going to see a few funny things about what people did to try to make the image smaller. Everybody who built a new telescope had a main technical goal of getting the images smaller to see what was really out there. You had to hold the telescope still. You couldn't put them out in the night and let the wind shake them. That was a big problem. And of course the Earth is moving. How are you going to keep repointing the telescope while you're taking notes and calling out numbers to people? It took about 4 people to make an observation in those days. And then it was a little hard to measure the positions of the stars because they didn't have accurate clocks. Now I want you to notice the date. This is a picture from a Chinese book that's explaining the Copernican system to the Chinese astronomers in the court of the emperor. The Earth is at the center bottom. The sun is the thing with little rays coming out of it near the top, and the little object going around it, half dark and half light, is Venus. This is 1626, 15, 16 years after Galileo had certainly demonstrated to his own satisfaction that the Earth was moving around the sun. But when the Jesuits presented this in China, the sun is going around the Earth. The magic here is that Galileo had discovered that Venus had phases. You can look at it one time of the year and it's half illuminated one way and another way another part of the year. Venus had to be going around the sun. In Copernicus' system, all the planets were going around the sun, and you wouldn't get, you would certainly get phases. In the ancient Ptolemaic system, with everything going around the Earth, you would not get phases. So with this single observation, it probably took 3 minutes each of 2 nights separated by a few months. Galileo completely wiped out all of ancient astronomy. But Tycho came up with this one solution that in astronomy we say save the appearances, right? Keep the ideas the same and still be able to explain the same data. So this is the so-called Tychonian system, sun in the center, with the, sun's the center of this picture, the Earth is off-center, but the sun is going around the Earth, Mercury, Venus, and are going around the sun, and then Mars is going around the sun, and then all the other planets are going around both the Earth and the sun. Okay? It's pretty simple, and it's all just to make sure that Venus has phases. This is a picture from 1650, a fellow named Ruccolo in Italy. I also got this from Owen Gingrich. This is Urania, the muse of astronomy, one of Zeus's daughters. Argus, the many-eyed, on the right. This is Ptolemy, the founder of the ancient astronomy, who is saying, I am improved by being shown wrong. Right? He's humiliated. And Urania is holding a scale. Right? And at the end of the scale is a Copernican system on the left and a Tychonian system on the right. And you see the Tychonian system is the one that's winning in this battle of weights. So this is still 40 years after Galileo made his discoveries. By 1650, Galileo had completely dissolved the ancient and perfect universe of Aristotle. Sunspots meant the sun wasn't perfect. Craters on the moon meant the moon wasn't perfect, and so forth and so on. So this was completely gone. And Milton and John Donne wrote wonderful poems about the devastation to the intellect of the day in seeing all the past understanding of the universe wiped out. Galileo knew that Copernicus was right. Kepler, the famous person who found that the orbits of the planets are ellipses and paved the way for Newton, knew that Copernicus was right, but they couldn't criticize Tycho. Tycho was too well known, too famous, and too much supported by the church. Tycho was a Protestant, and the Jesuits had actually managed to keep his books off the forbidden reading list because he supported their view of how the universe was made. So people want bigger and bigger telescopes, and now I'll start on the telescopes themselves. If you want a bigger optic, something to collect more light, Galileo broke the Milky Way into millions and millions of stars, and he was sure, as were other people, that if they could just look fainter at fainter stars, meaning they needed more collecting area in the telescope, they would certainly see many more, and who knows what wonders would be uncovered. The trouble was that to make a bigger aperture, say 4 inches or 7 inches, you had to have only very slight slopes on the lenses, so you had to have a very long telescope. Now they couldn't build stiff structures, they didn't have the engineering that we had, so the way they did it was to build a tower, put a little lens out here, have the observer sitting down here with a theodolite looking up with an eyepiece, and you can imagine the trials that he must have had. I think there were only 3 or 4 people who could actually make observations with this kind of a system. Helvius, on the European continent, built this long tube, which certainly would have flexed and blown around in the wind. Here's a picture of Danzig with this structure highlighted against the sky. This was 60 feet. The longest one ever built was 120 feet. I don't know if it ever worked. But you can see this is an elephant. It's not going to go, I mean a white elephant. It's not going to go anywhere. Well, people did get data. They figured out ways. They built really long telescopes if they wanted them to have large aperture. And they quickly noticed that the sky divided itself into 2 parts, round point sources and irregular fuzzy sources, only 2 kinds of objects. Right? And nobody made much out of this until it came to Immanuel Kant, 1755. Kant, in 1 page, said simply, these are all galaxies like the Milky Way. This is how they have to look. Okay? And on that day, the universe grew by an enormous amount because you had to have a universe big enough to fit in millions and millions of galaxies. I'll show you the impact of that in a few minutes. And it turns out what drove the rest of telescope development was the drive, technically, was the drive to get bigger apertures, better polishing, hold the telescope more still, all those kinds of things. But what drove the